Okay, well, I hope that everybody is having a good day. So, a few announcements. So, our plan today, we're going to go ahead and take a look at 2.12. It is a very short lesson, hopefully, a lot of review from Algebra 2, but we're going to be able to get it done today. One of the papers you picked up was the assignment for 2.12. That's going to be due on Friday. We got the assignment for 2.11. We're actually going to look at a few of the problems in just a moment. That is due on Thursday, so you still have a couple of days. But tomorrow, we've got our grade for the week. We're going to have a quiz over 2.9, 2.10. So you want to be looking ahead to that. I'm still here after school if anybody wants to come in, ask some questions. Unfortunately, tomorrow morning is the late start. So. And then coming up on Monday, April 7th, this coming Monday, from 5 to 7 over at Coronado, we have our third AP prep session. So I'll be mentioning this all week. If you can go ahead and think about tonight if you would be able to show up. You don't have to stay the entire time. You can arrive late. You can leave early if you need to. We would just love for you to be there. But I'm going to go ahead and ask tomorrow, try to get a rough head count so I can let Ms. Hanson know how many people we can expect, because we're also going to be trying to provide snacks for everybody. So from 5 to 6, we're going to be talking about identities and trig equations. And we haven't touched that material in a really long time. So I'm going to be reminding folks how to solve equations. We're going to be talking about the identities. That's my aspect of the evening. And then Ms. Wood is going to be taking care of sinusoidal models from 6 to 7. So a lot of really good material if you have the opportunity. Does anybody have any questions on that? Okay, well, before we go ahead and get started, let's take a look at that 2.11, which is right here. So I'd like to go through numbers 4 through 7. Okay. All right, did anybody need a copy of this? All right, let's do it. So it says the graphs of K and M are shown below. Use the graphs to answer the following. Okay, so number 4 says the graph of K is, and then it's either increasing or decreasing at an increasing or decreasing rate. Okay, so how would I approach a problem like this? Like, what do I do? I'm sorry? Concavity? Okay, so concavity is good. That doesn't apply to this problem, though. Like when we say at the very beginning of each statement, increasing or decreasing, that's simply referring to the y values. So as we're going from left to right, are your y values getting larger? Is it rising to the right? Is it increasing? Or as we go to the right, are they dropping to the right? Are they getting smaller? Are they decreasing? So what would you say this one's doing? Is it an increase or decrease? It's definitely a decrease. Okay, so now we can go ahead and eliminate A and B because it's not increasing. Now, what does it mean when it says increasing rate or decreasing rate? No, it's something specific. Think about that word rate. We're talking about slope, rate of change. So how is the slope itself changing? Is the slope getting larger or is the slope getting smaller? Well, for a curved function like this, the slope is constantly changing. So how are we able to kind of think about slope at an exact location? What was something we used? It was some kind of line. A tangent line. There we go. So what if I go ahead and draw a tangent line right here? Just one point of intersection. Well, this first one here tells me that we have a negative slope, but as I go ahead and start to draw more tangent lines, it's becoming less steep. In fact, the line is almost becoming horizontal. But what was the slope of a horizontal line? That's 0. Okay. So we're going from a negative slope to 0. So does that mean it's getting larger or it's getting smaller? Larger. There we go. Yeah, 0 is bigger than any negative value. So it's a decreasing function at an increasing rate. Remember, when it has that word rate, it is talking about slope, the rate of change. Okay, good, good. Now, I went ahead and copied another copy of that graph of K right there, so I don't have to keep scrolling up and down. Number 5 says, which of the following pairs of limit statements currently describes the end behavior? Okay. Currently describes the end behavior. Well, it looks like to me like we're looking at a logarithmic function. So where would you say the vertical asymptote is? Looks at 0, yeah, the y-axis. Looks like it's curving right towards that. Okay. So all 4 of these answers start off by saying the limit as x approaches 0 from the right. Okay, so we can't eliminate anything just based on the way they wrote it. But what's happening? We're curving up towards the asymptote, so what would be the answer to the left-end behavior? Is it curving towards positive or negative infinity? Positive infinity. Okay, so because A and B both say negative infinity on the left end, those are out. So it's got to be C or D. Let me go ahead and turn this down. But I did have it up because I'm sure you all know we lost power again during lunch. That was super fun. Okay. All right. My thinking is if the power goes out, why can't it just stay out? Maybe we'll get dismissed. But then we wouldn't be able to do math, and then everybody would have a horrible day. It's always consequences. Okay. Anyways, so what's happening on the right side as x approaches positive infinity? Is the graph curving up or down? Curving down, so the right end infinity is going to be negative infinity, so my answer is C. Good. Okay. Anybody have questions so far? We doing all right? Had anybody had the opportunity to look at this so far? Well, there we go. So we're already getting a little bit done. Okay, so number 6. Which of the following could be an equation for K? Okay. Well, you remember a second ago, I said this was what kind of function? It's logarithmic. Okay, so I can only look at a logarithmic answer. So in this case, C and D are out because those are both exponential. Okay, remember, the majority of your AP exam coming up on May 13th, 40 multiple choice questions. Okay, even if you don't have an idea of what to do, you don't have a strategy, or you might not remember the material exactly, whatever you can do to eliminate answers is always a great way to start. Okay, it's always going to get you close. So we've got -2 log base 4 of x or 2 log base 4 of x. How do I know which one could work here? Vera? Okay, so k is a decreasing function, right? So do I have a decreasing function as an answer? Okay. Well, you shook your head yes, but I guess I'm kind of confused. I'm looking at the bases. Both of these are 4. That's bigger than 1, so aren't these both growth? Okay, she says the coefficient is negative. Remember, we've talked previously, a reflection can take a growth, flip it, turn it into a decay. Okay, so that's what we're looking at. It's got to be A. Or a reflection could take a decay and make it into a growth. Okay. How are we doing so far? Good, good, good. And number 7, which of the following equations could be the inverse? Okay, well, let's go ahead and use the fact that we know we're dealing with a log once again to help us out. What's the inverse of a log? An exponential. So any answer that's a log function, I can automatically get rid of. Okay. So it has to be A or B. Okay. So I'm going to go ahead and get us started. Let me get this out of the way real quick. My function, and I'm going to go ahead and actually use the equation that we chose from number 6. So we've got y is equal to a -2 times the log base 4 of x. Okay. So what was the very first step if I'm going to algebraically find the inverse? What did I do? Switch the x and the y. Okay. So x equals -2 times log base 4 of y. Okay. So let me give you about a minute. See if you can figure out what the answer is going to be. All right. Got that on this timer right here. There. And then we'll go ahead and move on to 2.12. And if every other class is an indication, every other class had about between 10 and 15 minutes left at the end of class. But I know my 6th period, we want to start 2.13, right? Here we go. We know how to park. Oh, got your badge. Okay, so we'll go ahead and find that inverse in just a second, but who thinks they can help me out? Is the answer A or B? Let's do a poll. How many think it's A? How many think it's B? Okay, so we didn't have anybody vote for A. We had about 4 or 5 people vote for B. Okay, thank you. So the answer is A. It is A. Did anybody get that? Okay, so let's see what happens, because this one is kind of unusual. So we got to solve for y. The first thing I would do is go ahead and get rid of that coefficient. So let's divide through by -2. So a -1/2 x is now equal to log base 4 of y. So there's actually one thing I can do, and y is isolated. What am I referring to? I can take this log and what? I can rewrite it as an exponential. Okay, so I'm going to take base 4. Now remember, a log is a power, so whatever your log expression equals, that's the power I have to place on the base in order to equal the argument. Okay. Now, of course, your last step would be, once you get y by itself, to replace it with the inverse, so k inverse of x. But looking at my answer here, it says 4 to the -1/2 x. I said the answer was A. That doesn't look anything like that. So what's going on? Say again now. Okay, we can actually simplify this a little further using that -1/2. So we're going to be using the power rule. Remember, if I have, some exponential, and I go ahead and raise it, that's supposed to be an n, raise it to the power n, we're going to take a product, right? Well, remember, this rule is reversible. So why don't I go ahead and break apart this product? We'll apply the -1/2 directly to the 4 and have the x on the outside. So somebody help me out. What do I do to make a negative power positive? We got to flip it. You're going to take the reciprocal. Okay. So this is going to be 1 over, so 4 to the +1/2. But remember, raising anything to the 1/2 power, that's the same as doing what? Taking the square root. So the square root of 4, we got 1/2 to the power of x. There we go. So we did get the right answer. We just didn't simplify it enough to go ahead and find the answer that they had. Okay. How's that? Anybody have any questions? All right. Well, we already made a good dent into 2.11. We'll go ahead and talk about that again on Thursday. So you still got a couple of days. Let me go ahead and reset this. And let's get started with 212. You realize how close we are? I mean, just thinking about the big picture, including this lesson today, we are 4 lessons away from being done with the year's curriculum. Okay. Then it goes to review. We're getting ready with the test, FRQs, all that fun stuff starts. Has anybody started looking back over trig? We're going to do that soon enough, but what have you been looking at specifically? Identities? Just trying to remember those. Can we go ahead and recite them all right now? No. Okay, we'll get there. All right, so here's what we're doing in 2.12 today, log function manipulation. Okay, so since logarithm expressions can also be written in exponential form, the same properties that apply to exponents can also be applied to expressions involving logs. Okay, so you would have done this in Algebra 2 when you were solving, more complex exponential equations or even logarithmic equations. So there are 4 main properties we're going to look at. We're going to start with these 3. The product property, the quotient property, and the power property. Now, the product property says that if you have a product inside the argument of a log, if I'm multiplying two or more items together, I can go ahead and separate each of those items individually using addition. Each item is going to get its own log with the same base. The only way these properties work is if they have the same base. Okay. So multiplication goes hand in hand with addition. The quotient property, if I'm dividing terms inside the argument, I can separate those through subtraction. Okay, again, each individual term gets its own log with the same base. Now, this is very important. Order matters for the quotient. So the numerator, that becomes the first argument. It has to be written before the other one, the denominator. Okay, and then our power property, it says log base b of x to the n. So if I have an item with a power in the argument, that power can be pulled to the front where it becomes a coefficient. Now, all of these rules, they're reversible. So I can take an expression that's already expanded and I can condense it to a single term, or I can take a single term and I can go ahead and expand it. And that's actually what we're practicing today. Okay, let's get right into it. Example 1. For each of the following, write an equivalent expression by condensing each expression to a single log. Okay, so A says log base 4 of x plus log base 4 of y. Remember, you have to have the same base in order to do this. Okay, I've got two logs separated by addition. Remember, addition goes hand in hand with what? Yeah, if I'm looking at the very top of the paper, we're only separating by addition if we're originally multiplying. So these arguments that I have right here, x and y, I'm going to re-multiply those. Log base 4 of x times y. In the sink.
Yeah, now it's clean.
Okay, so that's where the water came from. Okay, just want to make sure. Okay.
Well, you know, it's not due to water.
Gotcha. It's going to be funny, the next person who asks in the 7th period to go to the restroom to touch it. Okay. All right. B, log base 3 of 5 minus log base 3 of z. Okay. So read, how do I recombine if we're separating by subtraction? There you go. So division, log base 3 of 5 over z. Now, could this have been z over 5? Why not? There you go. 5 was written first, so it has to be the numerator. There we go. Order matters when you're talking about that quotient identity. Okay, now for C, we've got 3 log expressions. So it actually does not matter where you start. I could go ahead and, let me use my highlighter here. I could go ahead and combine the previous two and then go ahead and merge in log of x, or I could go ahead and start with the first two and then take care of the last one. As long as I'm following the properties, it actually does not matter. So what do you say? We'll just go ahead and start with the left and work our way through. So don't worry about the log of z. I need log of x minus log of 5. And I'm not worried about saying base 10 because it's the common log. Okay, Quinn, can you tell me what those two logs will combine into? Okay, so we have log base 10 of x over 5, and then we have minus log base 10 of z. Okay. Now, we've got 2 more logs that are separated by subtraction, so I'm going to divide the arguments that I have. Okay, so we are going to end up with x over 5 divided by z, but let's simplify that. Can anybody tell me what my final answer is? Log base 10 of what? Is the x over 5? Very close. Very close. X over 5z. The z would have to go in the denominator. Okay. All right. Now, I'm seeing a couple of confused faces, so let's take a look. So I'm going to take this first argument, x over 5, and I'm going to divide it by the second argument, z. Okay, so we want to simplify this, so let's pretend that this z down below is a fraction. Remember, the rule, if we're dividing by a fraction, what do? We're multiplying by the reciprocal. So that means we're going to have x over 5 times 1 over z. So that's how I got the z down below. Okay. Why is it not a negative? What do you mean? Oh, you mean because of this negative right here? Now, you actually can do that. So if you pretend that this is a -1 in front of the log, you could view that as a coefficient, because if you're subtracting 1, isn't that the same as adding -1? So subtraction is just adding the opposite, right? So even if I were to go ahead and pretend this is a coefficient and put that -1 as a power on z to the -1, in order to make a negative power positive, I'm still flipping it and it still goes in the denominator. Or were you just talking about this negative, like why isn't my argument negative? That was your question? Okay. Does that make sense? Okay. Actually, I've only seen a couple of people actually bring up that idea today. You can choose or not choose to go ahead and bring the negative with it. Okay, very good. How we doing? Easy. How much of this is coming back to you from algebra? Good. Okay, well, let's take a look at D. So 3 log base 2 of x minus log base 2 of y. This is just like B, but there's something different. I can't combine them yet. I got to take care of one detail. What am I referring to? Okay, this coefficient. When you're condensing, if your term has a coefficient in front, you want to go ahead and pull that back into the argument as a power before you pull everything together. So this is going to be log base 2 of x cubed minus log base 2 of y. Okay. Once I've done that, now I can go ahead and combine them. What should be my final answer? Log what? There we go. Okay. So you're probably thinking to yourself, wow, this is super easy. I want to show off my skills to the class. Who would like to come up and show me E? So we need to condense 2 log base 7 of A minus 5 log base 7 of B plus log base 7 of 4. Okay, Wheel of Destiny. Okay, so I have to get to 16 seats in here. Oh, yeah, it got shut down when we lost power, so here we go. Okay, so we get 16. Let's go ahead and delete that. Let's give this a good shuffle. Okay. All right, who's going to come up and help us? Okay, William. All right. Okay, so William, help me out. Log base 7 of a squared. Right below the, yeah, there you go. You mean go straight to the final answer? I'm okay with that. And then if anybody wants to, I can run through that. So log base 7. There you go. Okay. So it should be 4 times a squared over b to the 5th. Now, if you did want to go ahead and rewrite that in a slightly different way, you could also say log base 7 of 4a squared over b to the 5th. Okay, good. Good. They're both equivalent. Yeah. Okay. All right, so did anybody want me to run through how we got here? Oh, how are those both the same thing? Well, because we're multiplying a whole number by a fraction. So we could go ahead and say 4 over 1 times a, that's a 2 right there, a squared over b to the 5th. All right. Nobody wanted me to run through that? Okay. Well, F. Now, F, I'm going to go ahead and have you try on your own. So we want to simplify this to a single log. And this question's come up, wait a minute, we don't even have another log to condense that with. So you're going to have to rewrite. Okay, so I'm going to give you a minute. Let's see if you can come up with the answer. What would 2 plus log base 6 of x look like as a single log expression? Okay, show of hands. Who thinks they've got the answer? Okay, William, what you got? Perfect. So it's log base 6 of 36x. How many people got that? Okay, so a couple hands are going up. Now, when I said we had to rewrite, I'm referring to the 2 right here, because these properties, they only work if you're interacting logs of the same base with each other. So I've got to rewrite 2 as a log base 6, right? But what is a log? Remember, it's a power, right? Okay, so whatever log expression I substitute here, it has to equal 2. Well, all we have to do, 6 squared will give me 36. Remember, that's what a log is, the power you place on the base in order to get the argument. So instead of 2, we got log base 6 of 36 plus the log base 6 of x. And because we are separating 2 logs with addition, we multiply the arguments together. Okay, questions? Okay. Now for the next one, we would take one that's already condensed and we go ahead and expand it. Okay, and I forgot to erase the answer from the previous class, so we know the answer is C, but did anybody have any questions about it? How many people would have chosen C anyway? There we go. All right. Okay, so we're just going to go ahead and kind of move past that. Save us a little bit of time. Example 3. The function f of x equals log of 6x is a horizontal dilation of the function g of x, which equals log of x. Show that f can also be written as a vertical translation of g, with f of x equal to g of x plus k, where k is just some constant. It's just some value. Okay. Well, this is just another way of asking you to expand using the properties. All I need to do is rewrite f so that I end up with a binomial, something like this. I want g of x plus k. Well, let's take a look at log of 6x. So log of 6x. Okay. So what do we do when we're multiplying in the argument? Do we add or subtract? Okay. I'll tell you what do we do. We add. So I'm going to take the 2 terms. This is log of 6 plus log of x. Okay. See, there is the sum that I wanted. Well, if you take a look, we've got the binomial we're looking for. Because right here it defines log of x is g of x, and that's what I've got right here. Okay. So log of 6, that's just going to be some number. We don't know what that number is, but 10 to some power has got to give me 6, right? So in this case, that's just some value. That's the k I'm looking for. Is everybody okay with that one? All right, now we're moving on to the 4th property, the change of base property. So let's say I have an algebraic expression, a logarithmic expression, log base b of x. I want to change its base. Okay? Now, I can choose whatever base I want, as long as I'm following these two restrictions. The base has to be positive and it cannot equal 1. Beyond that, there's an infinite number of ways I could do it. Now, look at the formula here. Log base b of x, the original argument x stays the argument in the numerator, but the original base, that becomes the new argument in the denominator. And then, of course, you go ahead and incorporate whatever base you want. Okay, so I've got an example to kind of help you see this. Log base 3 of 5, you can double check this in your calculator, but you're going to get approximately 1.46. So 3 to the 1.46 power is going to get me really close to 5. So what I want to do, let's go ahead and choose a couple of different bases and apply the change of base formula. Okay, somebody give me a base, as long as it's positive and not 1. 2. Okay, let's say base 2. So log base 3 of 5, if I'm going to apply this right here, well, up top, that would be log base 2 of 5. See, the original argument is still in the numerator, divided by log base 2 of 3. The original base is now the argument in the denominator. And it's kind of hard to see right there because I ran through it, but we chose bases of 2. Okay. Now watch what happens when I go ahead and plug this in the calculator. Okay, let me come on over here. Oh, yes. I don't have my calculator up because it shut down when we lost power. Okay, so give me 1 second. Maybe a couple. There we go. Okay, so let's see here. Let's go ahead and calculate this. So control divide. Let's put a couple of logs in here. So we chose base 2, and then the upper argument was 5, and the lower argument was 3. Okay, so somebody help me remember, what was log base 3 of 5? It was 1.46. So I applied the change of base. Look at this. Okay. You could do this an infinite number of times. You're always going to get the same answer, as long as that base you choose is positive and it doesn't equal 1. Okay. So this is our change of base formula. All right. Now, with this in mind, let's take a look at number 4. So it says let f of x equal log base 4 of x and g of x equals log base 9 of x. Show that f is a vertical dilation of g by finding the value of k such that f of x equals k times g of x. Okay. Now we're going to be able to do this because the note on the change of base formula, this property illustrates that all log functions are vertical dilations of each other. Okay. So if I have two completely different log functions, okay, I can transform one into the other simply by finding the right constant to multiply it by. Isn't that cool? It is. It really is cool. Yeah. Okay. All right. So for this one here, I want you to think about this one. This has been kind of difficult for some people today, this type of problem. I don't want to just show you and give you the answer. I want you to try to approach it. Now, you know for sure you're using the change of base formula on this. Okay. Kind of think about what we did in the previous problem. Okay. Let me give you 1 minute, and then we'll go ahead and talk about this. Now, if you're stuck, take a look at what they have here. You're getting f by transforming g. So I would start with function f. Okay. So remember, however I choose to rewrite this, I'm looking for a product that looks like this. where one part of the product is g of x. So I need log base 9 of x. So let's go ahead and apply the change of base formula. Now remember, I could use any base that I want. What base do you think is going to work here? Why 9? Because that's the base of the function we're transforming. Okay, so let's do this. If I go ahead and take log base 4 of x, I'm going to change the base with 9. So up top, this would be log base 9 of x. What's going to be in my denominator? Remember, the original argument stays the argument in the numerator, but what becomes the argument in the denominator? The original base. So this would be log base 9, that's a 9 right there, of 4. Okay. You've got your answer. Does anybody see it? Okay. Look at your numerator. What is log base 9 of x? Isn't that g? Okay. Well, what if I just took this fraction and I just went ahead and broke it apart? Because I can pull the numerator away from a fraction as long as I'm still multiplying. So I could say this is log base 9 of x times 1 over log base 9 of 4. See, right here, here's g of x. We ended up with the log base 9 of x that I was looking for. Well, we want to multiply that by some value k. Well, what do you think that is right there? That's k. So even if I were, it doesn't look like a constant, but if I were to plug it in the calculator, that is going to give me a value. It's going to represent some number, probably decimal, but that's okay. Okay, how are we doing? Anybody having a hard time? Okay, we're down to the very end here. The natural log. The log with base e is called the natural log. Now remember, log base e of x, that is technically correct, but e is such an important number to us that we have its own notation. So we don't like to write log base e of x. We prefer ln of x, the natural log. Okay, so here's my last example. We want to go ahead and find an equivalent expression to 3 natural log of x minus 4 natural log of y. Okay. Well, Akil, because they're separated by subtraction, am I going to multiply or divide these? We're going to divide. Well, that immediately eliminates a couple of answers. So what are we thinking? Would it be A or B? What's wrong with B? Because they still have the 3 and the 4 in there. There you go. Remember the power rule, it says that I can take a coefficient. I'm not going to multiply the term by it. I'm going to apply it as a power. So it would have to be x cubed and y to the 4th, not 3x over 4y. Okay. All right, there we go. Questions. How easy is that? Fantastic. Okay, we are done. Go ahead and shut this down. And let me make sure to erase